If you're listening to this episode when it publishes in July 2022, you are very aware of the fact that we are currently living through the COVID-19 pandemic. A pandemic that was formally declared a pandemic by the World Health Organization way back in March of 2020. And as of this recording, has killed over 6 million people globally and over 1 million people in the United States. But here's the thing about COVID-19. We have highly effective vaccines for it, and masking makes a huge difference when it comes to stopping transmission. My point is that although COVID-19 is still an infectious disease that you absolutely do not want to get, trust me on that, there are tools that we can use that make coexisting with it much, much safer. Now imagine an infectious disease that kills nearly a third of the people who get it, in a time when highly effective vaccines didn't exist, when the concept of a virus was still being worked out, and when there were no tools, like KN95 masks, to prevent getting sick.
The disease Sam's talking about is smallpox, or I guess we could say was smallpox, because it was officially eradicated in 1980. And today, it's still the only infectious disease in humans to have been eradicated. So, how'd we do it? And why haven't we done it for the many other diseases that plague us humans, like COVID-19? Welcome to Tiny Matters. I'm Deboki Chakravarti, and I'm joined by my co-host Sam Jones. Today on the show, we're talking about disease eradication. What made it possible with smallpox, what other diseases might be eradicated in the coming years, and why some diseases are just very hard to eradicate. And we want to give a shout out to Tiny Matters listener Diana Gibbs for suggesting this episode topic. If you think the 2 years of a pandemic have felt long, if we look back at history, it could have been a whole lot worse. Before its eradication, smallpox spent at least 1,500 years causing many, many epidemics. And across those epidemics, smallpox killed hundreds of millions of people, somewhere around 500 million in the 20th century alone.
Which is a number that I think is not even something that I could try to comprehend.
Yeah, I don't really know how to put that number into any kind of context. I mean, how do we get there? What is this disease? Well, smallpox is caused by a virus, and the symptoms are impossible to miss. There's the blistering rash, the high fever, and the severe body aches. If you got smallpox and survived, you'd likely be left with scars all over your body, and you might also go blind.
Smallpox also has a history of being used in bioterrorism. You might remember Deboki and me talking about this in episode 6 of Tiny Matters, mainly about how smallpox made it to the Americas by way of European colonizers who used it to kill native peoples. For example, in 1763, British General Geoffrey Amherst is documented to have ordered blankets from smallpox hospitals to be sent to native people in the area as a gift. Of course, knowing just how devastating that could be. Fast forward about 200 years, and the smallpox story has, I guess, as happy an ending as possible, because it's gone. On May 8, 1980, the World Health Organization declared that smallpox had been eradicated.
It's important to explain what that means so that we can talk about how we actually get there. When the World Health Organization declared that smallpox had been eradicated, that meant that there were 0 cases of the disease globally. There are some important stages before we get to eradication. One is disease elimination, which means the disease still exists globally, but it's been completely wiped out in a defined geographic area. And to get to the point where you're even talking about the possibility of disease eradication or elimination, you need disease control, which means reducing the incidence and threat of the disease. So that takes us back to the question we asked in the beginning. How are we able to eradicate smallpox, a disease that plagued humanity for over 1,000 years, but we haven't eradicated any other human infectious diseases? There are a bunch of different reasons, and one of them is vaccination. It's a story I think we really need to tell because the smallpox vaccine is considered by most to be the first successful vaccine ever developed. And it's where the name vaccine comes from.
So, for many, many centuries, people were trying to find ways to not die of smallpox. Historians say those efforts go back to at least 10th century China, when physicians started exposing healthy people to stuff from people with smallpox, meaning the pus in those smallpox blisters, which I know, sorry, it's very gross. I'm going to try not to say that word too much. So, the idea was that it would stimulate the healthy person's immune system and ideally help them build immunity. This is called inoculation, and it seems to have independently popped up in a bunch of different places across the globe over the course of many centuries. And sometimes it worked, but sometimes it just killed people and or would start a smallpox outbreak, which was the opposite of the goal.
Yeah, I think it would be kind of a bummer to be trying to stop an outbreak and instead create a new one.
Yeah.
Thankfully, in the late 1700s, things started to change. A guy named Edward Jenner in Gloucestershire, England, noticed that milkmaids, typically women working at a dairy farm, who had been exposed to cowpox, were not getting smallpox. Cowpox actually looks somewhat similar to smallpox, but your immune system can fight it off. Death is incredibly rare for humans who get cowpox, which is, of course, not the case with smallpox. So, Jenner wondered, could getting cowpox make someone immune to smallpox? He tested his hypothesis by inoculating an 8-year-old boy with pus taken from a milkmaid's cowpox sores. And it worked. Jenner referred to cowpox as variole vaccinae, Latin for smallpox of the cow. Ultimately, vaccinae was where vaccine came from.
So, the beauty of Jenner's method was that people were becoming more immune to smallpox without being exposed to the actual virus. Thankfully, things have greatly advanced since the late 1700s, and inoculating people with pus is, to my knowledge at least, no longer a thing. The smallpox vaccines that were used during smallpox eradication campaigns in the mid 1900s, especially the ones developed towards the end of the campaign, look a lot like vaccines that are still used today.
So, now let's talk about what it takes to eradicate a disease and what made it possible to eradicate smallpox. First, smallpox symptoms are very easy to recognize.
There's 100% clinical expression with smallpox. It's very hard to miss, and there's no subclinical infection. Occasionally, you can have a bad case of chickenpox. Occasionally, it can be confused, but really, smallpox stood out.
That's Myron Levine, who goes by Mike. He's the Associate Dean for Global Health, Vaccinology, and Infectious Diseases at the University of Maryland School of Medicine. Like he said, smallpox has clinical expression. There are very specific, defined symptoms that tell you that person has smallpox. And with smallpox, a person isn't contagious until sores start appearing in their mouth and throat. Compare that to diseases that are subclinical, meaning there aren't necessarily obvious symptoms. COVID 19, for example, can look like a cold or severe pneumonia or nothing at all. And people are still contagious when they're not showing symptoms.
Smallpox only being contagious once a person had symptoms was incredibly important for eradication efforts because it allowed for what's called ring vaccination, where people who may have been infected with smallpox but weren't yet contagious could be vaccinated before they were.
So, if a case of smallpox was identified, it was possible to go to where that individual lived and to establish surveillance. You would find out who all the contacts were. in the household, family contacts, a whole village. You could set up containment and you could vaccinate people even while they were incubating.
And actually, what's interesting with smallpox is that initially they tried to eradicate it with a mass vaccination approach, just trying to get everyone to get vaccinated. But still, most countries were only seeing about 80% of people get the vaccine.
You keep vaccinating the same people and you miss the people who, for whatever reason, are isolated or don't want to be vaccinated. And that led to the concept of surveillance and containment.
Without ring vaccination, smallpox probably wouldn't have been eradicated, or at the very least, it would have taken a whole lot longer. All right, Deboki, what are other things that led to eradication?
So, another aspect to smallpox infection is that it doesn't involve any animal reservoirs. Smallpox can only be passed from one human to another, unlike something like malaria, which mosquitoes transmit between people, or COVID-19, which has now been detected in multiple animal species. And then, aside from the virus itself, eradication happened because people worked together to make it happen. This required global coordination. If the goal is 0 cases across the entire world, then the entire world needs to work together, which isn't always easy. There needs to be political support and effective distribution of resources. The fact that smallpox left people with scarring or blindness, and that it had killed so many people for so long, meant that, in Mike's words, there was global buy in.
Even though smallpox is the only human disease that has been eradicated at this point, there are many other infectious diseases that scientists are hopeful will be eradicated, or at the very least, eliminated in certain regions in the coming years. One of those is polio. 2 of the 3 viral strains of polio have been eradicated. And in the US, all polio strains have been eliminated. But one remaining strain of poliovirus still causes the disease in other parts of the world. Actually, when I traveled to Bali a few years ago, I needed to get a polio booster before going because they just had their first case since 2006. Keep in mind that global cases have decreased by 99% since the late 1980s, from hundreds of thousands of cases to just hundreds. But of course, for something to be eradicated, that number needs to be 0.
Right now, the disease Mike is most focused on controlling and working towards eradicating is typhoid fever. We focused on typhoid in episode 4 of Tiny Matters, so if you want to go on a deep dive, definitely check that out after this episode. Typhoid fever is caused by bacteria and typically spreads through water and food. There are vaccines for the bacteria that causes typhoid, and new iterations are getting better at protecting young kids who are some of the most vulnerable to the disease. Antibiotics can be used once someone's sick, but that's led to antibiotic resistance in a lot of places. But Mike told us that's fortunately not the case where he's currently working to eradicate typhoid.
I'm working in conjunction with the government of the island nation of Samoa on the concept of typhoid elimination in that population. Their endemic typhoid on these beautiful tropical islands are completely sensitive to every antibiotic. We don't know how or why that has managed to stay, but so far that's true. And so we're in the midst of intervening with vaccine, and then we hope in what's called a consolidation phase to actually visit every village and, in theory, every household to test and try and find the chronic carriers. We can either successfully treat them or we can at least let them know they must be very attentive to hand washing and food preparation. So this is one of my bucket lists, is to see if we, in that isolated island nation, whether we can use all the tools we have to actually interrupt transmission and then find the reservoir. That would be very special.
Another disease that you often hear talked about in the context of disease eradication or elimination is malaria, which is caused by parasites that are transmitted between humans by mosquitoes. So, when a mosquito with malaria parasites bites you, the parasites enter your body and multiply first in your liver and then in your red blood cells, where they grow and then destroy the cells, releasing more parasites, then invade other red blood cells, and continue the cycle. In addition to flu-like symptoms, vomiting, and diarrhea, malaria can cause anemia and jaundice, a yellow coloring of your skin and eyes. So, let's talk about current strategies for dealing with this infectious disease.
One of the ways that you can control malaria transmission is that when someone gets infected by parasites, if you can identify, diagnose that infection, and then treat them with medicine that will clear the parasites from them, then if they're subsequently bitten by mosquitoes, those mosquitoes won't be able to pick up parasites and transmit it to anyone else.
That's Michael Santos, who's the VP for Science at the Foundation for the National Institutes of Health and director of the Gene Convene Global Collaborative. He told us that treatment post infection is overall very effective at curing people if they're diagnosed early. But some malaria parasites have developed resistance to those treatment drugs. There's also a malaria vaccine that helps kick your immune system into high gear if you're exposed to malaria parasites, fighting them off before you get really sick. The vaccine is helpful, but it's far from perfect. Michael told us that at this point, the most effective measures for preventing malaria have been targeted at mosquitoes.
You can try to remove parasites from infected people. You can try to protect people when they're bitten by an infected mosquito, or you can just try to stop them from getting bitten by mosquitoes. That third approach of stopping people from being bitten by mosquitoes, which has been responsible for the tremendous progress that has been achieved in the 20 years from 2000 to 2020, the rate of death due to malaria dropped by about half. And the majority of that improvement was attributed to two interventions.
Those two interventions were: one, mosquito nets treated with insecticides to keep people from getting bitten while also poisoning the mosquitoes that land on the net, and two, spraying insecticides inside the walls of a home. Michael told us that after a mosquito feeds on someone's blood, the mosquito is really heavy, so it won't go far before resting. And if it stops to rest on a wall that's sprayed with insecticides, it'll die before it can transmit malaria to the next person. But even with all of these prevention and treatment measures taken, malaria is still out there, and progress on controlling it has somewhat plateaued, in part because mosquitoes are becoming resistant to the insecticides sprayed on bed netting and walls. So, researchers like Michael are looking for other solutions.
One of the areas that has a lot of potential for impact is to use genetic strategies to engineer mosquitoes in a way that will either reduce the number of the mosquitoes that spread malaria, or that will make it so that even if those mosquitoes bite an infected person, they're not capable of transmitting that malaria infection onto someone else. The initiative that I direct, the Gene Convene Global Collaborative, has as its mission to support informed decision making about these genetic biocontrol approaches for public health, and the main area that we work on is malaria.
There are different genetic approaches that people are exploring. They might involve genetically engineering mosquitoes to not have offspring, or they might involve a technology called gene drive, where genetic changes are introduced into mosquitoes, changes like the inability to transmit malaria, and those changes get passed down so that eventually we have generations of mosquitoes that cannot transmit malaria, and the disease, hopefully, fizzles out.
Looking ahead to malaria and thinking about the wide geographic coverage that malaria has, and thinking how are you going to get to actually zero in the world, it will likely be important to have interventions that can be very effective in places where, for conflict or other reasons, it's harder to reach them with some of the more conventional interventions like vaccines or diagnosis and treatment. And that is one of the probably unique advantages that approaches like gene drive have, because it is possible for these genetic changes to spread and persist in the environment on their own, even in places where humans cannot otherwise easily intervene.
At this point, research on gene drives in mosquitoes has been going on for years in the lab, and it seems to work really well. But that's just the start. Depending on the country, state, even county, there is extensive safety review before engineered mosquitoes would ever be introduced into the wild. So, polio, typhoid, malaria, and other diseases might one day, not so far from now, be eliminated in places they exist today. Maybe even one day they'll be eradicated. But what about COVID-19?
We have good vaccines to prevent COVID deaths and hospitalizations. We have people who are completely against COVID vaccine and other vaccines. Some are hesitant. That is a huge problem. And that is aside from the fact that if this virus is becoming adapted to the human population and is becoming an endemic virus that, like influenza, will drift every 2 or 3 years, I do not see that this is going to be on our list of high priority diseases to eradicate.
The whole COVID-19 situation right now is a lot of things, including incredibly frustrating. But I want to wrap up this eradication story with some good news. In the last week before this recording, COVID-19 vaccines were approved for children ages 6 months to 5 years old. That is something to celebrate. All right, so I think that means it is time for our tiny show and tell. Deboki, do you want to kick it off this time?
Sure.
All right,
I mean,
awesome.
one of these days I'm just going to say no, I refuse, but not today. Okay, for my tiny show and tell, I want to talk about seagrass, which is not necessarily as well known as seaweed, but they are actually very different things. Seagrass is actually descended from a land plant that was like, hey, I'm going to go back into the ocean and I'm going to thrive. And seagrass actually grows into these really large meadows that end up being really important to a lot of wildlife in the ocean, which I think is really cool just because the ocean is so vast.
Yeah.
And there's so many weird things growing in there that, make homes for other things. One way that seagrass grows is through sexual reproduction, but it can also reproduce asexually by basically cloning itself. So it just makes these little shoots that end up branching off of the same root system, and that's how these big meadows grow. And I bring all of that up because scientists were studying 10 different seagrass meadows in Shark Bay, which is off the western coast of Australia. So they were studying these genes from different seagrass meadows in the area, and they were surprised when they realized that a lot of those seagrass were genetically identical, even if they were coming from different meadows. They were clearly all clones of each other, which means that basically off the coast of Australia, we have 77 square miles of a carpet of clones. That's how I choose to think about it. And so depending on how you define things, that means that you could potentially call this the world's largest organism. And there is some competition for that title. There's a colony of aspen trees in Utah that are connected together. And there's also the aptly named humongous fungus in Oregon. And those are all, they're big. They take up some space, but still smaller. They're still both way smaller than 77 square miles of clonage. So I just love the idea that, you just find a lawn of clones off the coast of Australia.
Yeah, it's very fun, and it's definitely, I think, the basis for a very interesting bar conversation if both people are super into science stuff.
Yeah.
Otherwise, it sounds like horrible for anyone else who's around.
Yeah. You have to both be willing to argue about semantics for hours on end, which I'm always up for.
I was going to say,
I don't know
I'm
that
game.
everyone I know is, but
Yeah, absolutely. That's really cool. Well, thanks, Deboki. I will do mine now. Okay, so mine is about microscopic mites that live in the pores on our faces. The first ever full DNA analysis of these mites was just done. There were a lot of different findings, but I'm just going to give you some of the take-homes. So these mites, they live in our pores and they mate on our faces at night. And it seems like they're becoming more and more one with us, meaning we're really symbionts. Like they're helping us out, we're helping them out. So essentially, they're passed on during birth, like when we're born, and they're carried by almost every human. And as our pores get bigger, there's more of them. They're around 0.3 millimeters in size. You cannot just see them. And they just kind of eat like the dead cells and stuff in your pores, which is kind of awesome. You know, they might be really helping you not get acne or some sort of like infection or whatever. They're not dangerous. They're not bad for us. I'm going to Slack you right now, Deboki. I have an image of them ready to go for you because
Okay,
I
I'm
was
so
thinking
excited.
Deboki's going to want to see this. She's going to ask for it.
I sure am. Oh my God. Oh my God. What is that?
That's a mite. The little circle, that's a mite.
It just looks like a little worm. The moment the right person or the wrong person hears about this, like mite facials are going to become a thing. Like,
Oh, you're right. You're so right. I didn't even think about that. Someplace right now is adding it onto their list of facial services.
I love that.
So there we go.
That's amazing. Thank you so much.
Of course.
I'm not going to look at my face the same way again.
I know it took me a day of not being like, how many mites were reproducing on my face last night, but it's fine. Thanks for tuning in to this week's episode of Tiny Matters, a production of the American Chemical Society. I'm your exec producer, and I am joined by my co-host, Deboki Chakravarti.
This week's script was written by Sam, edited by me and by Matt Radcliffe, who's the executive producer of ACS Productions. As always, it was fact-checked by Michelle Boucher. The Tiny Matters theme and episode sound design are by Michael Simonelli, and our artwork was created by Derek Bressler.
Thanks so much to Mike Levine and Michael Santos for chatting with us this episode.
As always, if there are some tiny things that you think matter and that you'd love us to explore in an episode, shoot us an email at tinymatters@acs.org. You can find me on Twitter at okidoki_boki.
And you can find me on Twitter at SamJScience. We'll see you next time.